let me continue with the pseudo inverses. So the pseudo inverses is something which should be very similar to inverses, and it's a nice thing, as you will see. It again will be based on the singular decomposition in a very straightforward way. So what are the pseudo inverses of matrices? So you see, as we have heard in the last presentation, so every matrix A with m rows and n columns can be put into a diagonal form, choosing orthonormal basis in the beginning and the end, right? So we take the scalars with the standard scalar products. So it's not the scalars, but the k to m and k to n with the standard scalar products, and what we get is the choice of suitable basis in which a given linear map has got diagonal form. Very nice. And now what we can do is, we know that D is a diagonal matrix with positive real numbers on the diagonal, so we can invert the D. That's not a problem. We call it S dagger. So of course it's not the inversion of S. So first of all, S is not at all square, so it in general can't have an inverse. And second, there are the zeros here, so even if m was n, then there are the zero eigenvalues possibly there too, so there can't be the inverse matrix of S. But we can define this S dagger as something which is as close to the inverse as possible, and then we simply use the same basis but in the beginning. So it was phi going from V to W, so I'm sorry, so this V is a vector space and this V is a matrix, so sorry for that. And we have got the phi star, which goes from V to V, and actually we don't want to have the phi star here, but there will be now the dagger here. And so it goes, if we just change the basis, so we have to use the inverses of the previous changes, right? So here it was the matrix V star, which changes the basis in the target, which is the inverse of V, so we write V here, and here will be the inverse of U, which is U star. So the right definition for the A dagger is, we take the S dagger as something which is as close to the inverse as possible, and we go back to the original coordinates with the inverses, and this is called a pseudo inverse matrix. And now, as you see, it's just based on the singular decomposition theorem, but it has got very nice history, but more interestingly, it has got very nice properties. And the most important property is the property 4, because whenever you write down linear equations, you know that the image of the mapping, which is depicted in the left hand side by A times X, right? So it eats X, produces A times X, which is the same thing as thinking about the linear mapping eating a vector and producing the value. And now we prescribe the value to be B, but the B might not be in the image of the mapping, which is a problem. Then the solution doesn't have any solution. But if we if the A was a square matrix, and if the B was in the and if it was invertible, then of course it's a bijective mapping, and for each B there would be just one solution, A inverse of applied to B, right? It's like with the scalar. So if you want to see that Y is A times X, so A times X is Y, I don't know the X, then I can compute the X being Y divided by A, right? So and here we do the same, but we have to take care from which side we multiply with the inverses. And what we can do is, we can take the B and we can hit the B with the pseudo inverse, which gives us some prospective solution, right? So we don't know. But what we do know by the theorem, and it's a straightforward consequence of how it was constructed is that what we get, this y, is actually the minimizer of the distance. So what we get is, you can imagine if it was in R3, so we would have, say, a mapping from R3 to R3, and the whole value of the mapping would be some subspace. So say the whole mapping would just be, so the whole space would be mapped into the xy coordinates, right? And now I want to get some b here, and I know that the image is only what I get here down. So what I do is I take the orthogonal projection, and this is the image which is closest to my prescription, right? And I take the pre-image of that, and so and that's one of them, right? So here in my case, but definitely I get some, so that will be the y, and in the end of the day I get the best possible approximation to a solution. So that's how the pseudo-inverse matrices work. And now let's have a look how close they are to the inverses. So first, if A is invertible, so necessarily it must be a square matrix, then we just recover the original inverse. So there is no change. So that's a good sign, right? So we are on the good track to have a nice generalization of the inverse matrices. Next, I mean, if it was an inverse, then these two things were unit matrices. Well, we can't get there in general, but what we can get, so notice if the sizes of the rows and columns are different, then also these matrices are different, because those are square matrices. The first one has got the size of the rows, and the second one the size of the columns. And whatever we choose for A, so this products will be always Hermitian. So in real case they will be symmetric. So they are simply self-adjoint. So that's the generalization of being unique matrix, right? Unit matrix is a special case of self-adjoint. And moreover, of course, if this was a unit matrix, then of course these two things must hold true, but they hold true all the time. So this is the similarity to the inverses. So then the third claim is that actually, as usual in mathematics, so if you were on the other side, not coming from the singular decomposition theorem, etc., then you might be interested in generalizing the inverse matrices, and you would perhaps just come up with the idea, why not to request 1 and 2? And then the 3 says that actually these two properties uniquely pin down the concept of the pseudo-inverses, right? So it means that if you find some matrix of the right type, which has the properties that the products BA and AB are both Hermitians, and the second property also holds true, then you already know that it must be the pseudo-inverse we have defined via the singular decomposition. And 5 says what are all the solutions, right? In 4, and on the picture here on the left hand side, I was finding the right image, and the pre-image of this as the set of all the solutions which will be approximating best the prescribed value B. And here you have a formula what are all of them, right? So it's not so difficult to see. So you simply take the kernel and you can you add all those which are mapped to 0, right? And that's exactly here. So this is our say introduction to the numerical things with matrices, and you see the proof is not not complicated, it's just straightforward computations, but it takes some time. So you are invited to go through. Right, and then there is some simple glimpse or glance towards some applications, so you can just have a look at it yourself. And this is what I prepared for this week. Thank you.